me show you how to get the browser that you need on your computer. So if you go to just on your syllabus page, your home page here, if you go right here, it says Lockdown Browser Quiz. Okay, so I'm going to get into the student view so you can see how this looks when you click on it. If you go to that, click on that, it takes you here, say take the quiz. This isn't actually worth anything. It's not worth any points or anything. It's just for you to simply get the browser. So here it says you can't take it because you're not using the Lockdown browser. So you click on that to download the Lockdown browser. Okay, you follow the instructions, and then you will have an icon on your desktop that looks like this. Okay, actually yours might look, yeah, it's about like that. Okay, so you'll be able to open that. Okay, it might tell you to close certain programs on your computer, different things, but if it's ready to go, so I have to close Snagit. No, I don't want to close Snagit. But what it would do is it would open up the browser to ACES. Okay, so it'd take you to ACES. You'll be able to log into ACES, and then from there you could go click on that quiz again. Once you're in the Lockdown browser, make sure you can pull it up. If you can, then you did it right. If you can't, then something's going on. Just bring your computer on Monday and you know, try to do it again, and or with me around. Come in a few minutes early. Let's get you started. Okay. If you're here early, you can get started early. I'll try to be here in the classroom at least 15 minutes before class starts, so that if you're here that early, then you're going to have that much extra time to take your test. Okay. If you're here late, then you have less time to take your test because the test cuts off exactly at 9:15. Okay, so at the end of class, it'll cut you out. You won't be able to do anything else. It'll submit your quiz, just like on your homeworks and such. Okay, so make sure you're here on time, if nothing else, or early, so you can get any issues worked out. If you don't have a computer, I will have a computer available. And all your reference material are found on the test. So if you actually go to the so the test is now on Canvas. It's not going to let you take it because you don't have the code, but okay, but you'll be able to see these things like the reference material. So if you click on that, it's going to take you to a link and show you what reference materials will be available to you, okay, for this test. So this is for all the tests. You'll have these, but you're not going to need them for all those for this test. Just chapters 1 and 3 basically. You'll need those equations and things, some of these conversions. So, and if you're taking the test and you're like, oh, I feel like you should have given us this reference material, Mr. Crandall. Okay, I'll go ahead and type it right on there. I can edit this form right here from here, and you guys can see everything I do. Okay, so if you feel like something's not there and I should have had it, that's how a lot of these conversions got added. People are like, Mr. Crandall, you didn't give me this conversion. I'm like, okay, I type it right on there. This is what it is. Okay, so if you come across that situation, but hopefully you won't because we've vetted it already. So I think we've got everything on there that we need. Hopefully you won't run into that situation. Make sure you bring a calculator. A calculator is going to be necessary. Here's the periodic table that you're going to be provided. Okay, so you might say, oh, that's really small. I can't see Mr. Crandall. Okay, well, just make it bigger or smaller. Okay, if you can't do it with your fingers, then you can just go to view and you can view it at different sizes. Okay, whoops, that was the same one, and that will allow you to view it bigger and to see it. Okay. All right. Somebody else is already on here with me. Okay, that's cool.
Can we print these documents as opposed to using them?
You can't print them and bring them in yourself because I'm not going to be able to check everybody's papers they bring in. If I allow you to open it right here, I know it's an unaltered copy and that it's Okay. So no, I'm not going to allow you guys to bring in your own things. Okay. But these will be available to you on the test. You'll be able to access them. If you're using a PC, then it'll just simply be another tab. You just click on the tab. From the tab you're using for the test, click on the other tab, that's your reference materials, and you'll have those available. If you're using a Mac, then for some reason, I don't know why, it makes you open up a whole new window to see the reference materials. And it's a little harder to work with because you have to close that window, go back, and then open it again. But those are always there. That link is always there for you to click on and get back to it. Okay? And, all right. And you should be familiar kind of with the tests, the way that's set up because you've been doing the homeworks, and it's pretty much kind of the same setup. Okay? All right. Let's go ahead and get started now to finish up Chapter 3. Okay? We don't have much left, but we were talking about molarity. So here, we're looking at how do we calculate. This is using the equation for molarity. Molarity equals moles per liters. And the question here is how many grams of sodium chloride are contained in 2.50 liters of a 5.3 molar solution. So we want to find the grams. What do I have to, using this equation, which of these do I solve for to get grams? Do I solve for molarity? Do I solve for the liters? Or do I solve for the moles? The moles. Because moles can be converted to what? To grams. So I solve for the moles. They gave me the liters and the molarity, right? So I move the liters up. Moles equals molarity times liters. Okay? So my molarity is 5.30 molar, and my liters are 0.250 liters. Okay, what is that? Who can tell me? 5.3 times 2.50? 1 point what? 325 moles. Okay? So those are my moles. That doesn't answer the question though, right? The question is how many grams? So we're going to go to the grams from the moles. And this is for sodium chloride. Sodium chloride. So we have to find the mass of sodium chloride. Sodium is 23 grams. This is 35.5. Okay, so sodium chloride has a molecular mass of 58.5 grams per mole. This is grams per mole. So that's the conversion I'm going to use here. 1 mole has 58.5 grams. Okay, so now I'm simply going to take my moles and I'm going to multiply it by my grams. 1.325 moles. The moles cancel and I'm left with grams times 58.5. What do I get? I'm sorry, say it again.
77.51.
Okay, 77.51 grams. So that's how many grams of sodium chloride are contained in 250 milliliters of a 5.3 molar solution. 5.3 molar is pretty concentrated, so you would expect a pretty good amount of grams. Okay? All right. So it's simply knowing the process. What am I going to solve for? And then I have to convert to grams, from moles to grams. Okay? This up here. Okay. If the typical concentration of vinegar is 0.839 molar, what volume of vinegar contains 75.6 grams of acetic acid. So what am I solving for? Volume. Okay. What? So I'm going to use the molarity equation equals moles over liters. I want to solve for volume. If I move volume up, we know that moles equals molarity times liters, and I move molarity down. So therefore, moles over molarity will equal the liters. Okay, the volume. So this is the equation I want to use. So I need my moles and I need my molarity. Do I have the molarity in the question? Did they give me molarity? Yeah. Did they give me the moles? No. So can I find it? Good. So I'm going to take my 75.6 grams of acetic acid. Okay? And acetic acid is CH3COOH. That's the molecular formula for it. Okay? So I have C2H4O2. And I think we did this in an earlier question, if I'm not mistaken. Let's see. Where is it? Okay? Right there. 60 grams per mole. Okay? So it's 60 grams per mole. That's what we decided earlier. We figured that out. Okay? So 75.6 grams of acetic acid, and I want to convert that to the moles from the grams. So I'm going to have every 60 grams for every 1 mole. So how many moles is this? 75.6 divided by 60. What do I get? Okay, I'm sorry, that's moles. Moles. Okay, now I have everything I need, right? Now I can easily solve for the liters. So, liters equals moles over molarity. The moles are 1.26 moles. The molarity was 0.839. 0.839 molar. Okay? Well, am I left with liters if I do that? Let's see. So molarity is moles per liters. So if my liters end up all the way down here, I actually put them to the top. So it's going to be times liters over here. I'm just going to move them up. And my moles cancel, and I'm left with liters. Okay? So it does work. I did isolate my liters. What is it? 1.26 divided by 0.839?
1.50.
Liters. Okay? And they didn't say milliliters or anything like that. They just said volume. Okay. So we're okay. So that's how many liters we would find. Okay? Okay. Now that's molarity. Now we're going to talk about dilution. Dilution is the process of taking a concentrated solution and adding water to it, or adding solvent so that the concentration changes. It was a really concentrated solution. You add more water and it becomes less concentrated. Okay? So if I think about that, so let's say I have a solution here. Let me just draw this bigger. Okay? With 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say those equal moles. There's 10 moles of something dissolved into this solvent. Now, if I add water to this, okay, and I dilute it up to here, so it was there, now it's here, did the number of moles change? No. The number of moles is constant. It stays the same. What changed was the volume and the concentration, because now these can spread out in that new volume, so they're less concentrated, right? They're less concentrated. So with that, we get a really easy equation to be able to calculate dilution, because moles equals molarity times the volume, or liters, okay? That's what it equals. So the initial volume and molarity are equal to the initial number of moles, and the new volume and molarity are equal to the new number of moles, because the moles don't change, right? This number is constant. It doesn't change. So this is the equation we end up with right here. The moles and volume of the first solution are equal to the moles and volume of the second solution. So let's think about what that means. Okay? So if I, okay, so there's my equation. So if I have, let's look at this question. Okay? If 0.850 liters of a 5 molar solution of copper nitrate is diluted to a volume of 1.8 liters, what is the molarity of the new diluted solution? So I have my equation M1 V1 equals M2 V2. Okay? This is my dilution equation. And I can identify the initial molarity and volume and the new volume, but not the new molarity in the question. So that's what I'm solving for, right? What is the molarity of the diluted solution? So I know what I'm solving for, M2, and I can easily see what the equation to solve for that is. Okay? Because M2 equals M1 V1, and bring V2 underneath, right? M2 equals M1 V1 divided by V2. This is what I'm going to use to solve for this question. Okay? I'm going to identify everything. This is M1. This is V1. Okay? This is V2. Now, in this situation, the volume is in liters. And with the molarity equation, you have to have the volume in liters. But with the dilution equation, you don't. It's in liters, so my answer, that's okay. I can leave it in liters. But if it was in milliliters, as long as both volumes were in milliliters, that would be fine. Okay? It wouldn't matter whether it was in milliliters or liters. Let's try it in both situations. Okay? So here I have the molarity to be 5 molar times 0.85 liters divided by 1.80 liters. And this is going to equal my new molarity, which is what? Okay, 2.36. Now let's suppose it was in milliliters instead of liters. 5 molar times 850 milliliters divided by 1,800 milliliters. Is my answer at all different? Can you see why? Because it's a ratio. It's a ratio. The ratio doesn't change. 0.8 divided by 1.8 is exactly the same as 850 divided by 1,800. Okay? So as long as your units cancel correctly, it doesn't matter whether you're using milliliters or liters when it's dilution. When it's molarity, it does matter. You have to use liters. But in this one, you don't. Okay? You don't have to. Okay. So this is going to be 2.36 molar as well. Either way, it's exactly the same. What volume of 0.12 molar HBr can be prepared from 11 milliliters of 0.45 molar HBr? Okay, so they actually gave me the milliliters and the liters here. Okay, so which one do I use? It doesn't matter. If you use the milliliters, your answer will be in milliliters. If you use the liters, your answer will be in liters. Okay, so that's the story. So I'm looking for the volume of a 0.12 molar. So this is V2 and M2. And this is my V1 and my M1. This is my initial volume and molarity. Now you'll notice in dilution equations, you always have a pair of things. This is a pair, and this is the lone person. You always multiply the pair together and divide by the other one. The pair is always multiplied together, and you divide by the other thing. That's how you do dilution. Okay? So 0.45 molar times 11 milliliters divided by 0.12 molar HBr. Okay? If I solve it out here, M1 V1 equals M2 V2. I'll be solving for V2. Okay? V2 equals M1 V1 divided by M2. I just bring this M2 down and I isolate V2, right? So that's what I'm doing here. M1 V1 divided by M2. So 0.45 times 11 divided by 0.12. What do I get? 41.25 milliliters. Now, if I had used liters, I would say 0.45 times 0.011 divided by 0.12 molar. This is molar. This is liters. Now what's my answer?
Same.
It's not the same. What is it?
0.041.
Okay? But it's in liters. Now it's in liters instead of milliliters. If I do it this way, it's in milliliters. If I do it this way, it's in liters. Okay? So, if you're using liters as your units, your answer will be in liters. If you're using milliliters, your answer will be in milliliters. So it's simply what you're trying to get. Am I trying to get the milliliters or the liters? Okay? And you can always convert from one to the other if you needed to. A laboratory experiment calls for 0.125 molar HNO3. What volume of 0.125 molar HNO3 can be prepared from 0.25 of 1.8? What's the pair? What is the pair that I'm looking at? Find the pair. What is it?
0.25 and 1.8.
Yeah, there's my pair. So I multiply those two things together. What am I going to divide by? 0.125. And that's going to give me what volume? What volume of HNO3? Okay? So 0.250 liters times 1.88 molar divided by 0.125 molar. Molarities cancel. I'm left with liters, which is what I want. And what is it? Say it again? Sorry, silly.
3.7.
Thank you. 3.76, whoops, liters. Liters is what I need. Okay, so find your pair, divide by the other thing. That's going to solve for that missing item, whatever you're looking for. What is the volume? Okay, now dilution can be a little tricky sometimes if it's a question more like, so if I had altered this question to say, how much water would I need to add to make a 0.125 molar HNO3 from 0.25 of 1.88 molar. Okay? So I'm starting out with a 1.88 molar, and I'm going to go to 0.125 dilution. How much water would I need to add to the 0.25 liters to make it a 0.125 molar solution? So the difference here is that the question isn't asking what's the final volume, it's asking how much water do I add to make it that. Okay? So my final volume is 3.76. How do I find the amount of water to add? Yeah, I subtract 0.250 liters. So how much water do I need to add? Because 3.76 liters is the final volume. I'm starting out with 250 milliliters. 3 point what? Liters. So I need to add 3.51 liters to 0.25 liters to make this solution 0.125 molar. Okay? So that might be the only thing that's really kind of tricky. You need to read the question carefully to make sure you're not getting a question like that. Because then you'll solve for 3.76, but the answer is actually 3.51. That's how much water I should add. The final volume is 3.76. If it's asking for the final volume, that's fine. But if it's asking how much water you should add to 0.25 liters, you need to say 3.51. Okay? Okay, how much 1.59 molar potassium hydroxide is required to prepare 5 liters of 0.1 molar KOH? Okay, where's the pair? There's the pair, and I'm going to divide by this, and it's going to give me the volume. Okay? So that's dilution. Dilution is not difficult. Okay? It's a very straightforward equation. M1V1 equals M2V2. You always find your pair, divide by the other thing. And because you're always solving for something unknown. And so there's always going to be a pair, and you're solving for the other thing. Okay? All right. I think we've got the idea. Here's my pair, and that's the other thing. So my answer is going to be in milliliters. My answer is going to be in milliliters for this one. Okay, now, other concentration units that you would encounter are things like, so we've looked at molarity. That's moles per volume. Okay? Now we're going to look at mass per mass percent. Mass per mass percent is simply defined as the percent or the mass of a solute. The solute is the thing in the lesser amount. And you divide it by the mass of the entire solution and multiply by 100. That'll give me my mass per mass percent. Okay? If it was mass per volume, parts per thousand, you've heard of that, parts per thousand, probably for like your drinking water or parts per million. Something in your drinking water is parts per million or parts per thousand. Okay? Well, that's simply a mass per mass ratio times 1,000 instead of 100, which is mass per mass percent. So this is parts per thousand. Parts per millions would be mass per mass times 1,000,000. Okay? And that's how you would calculate those. Mass per volume percent is the mass of the solute over the volume of the solution. Okay? Now, the trickiest thing for these, so this one's going to be really easy, I think, to calculate. But the trickiest thing for mass per mass percent is this mass of solution. Okay? So let's look at an example there. A 5-gram sample of spinal fluid contains 3.75 milligrams of glucose. What is the percent by mass of glucose in spinal fluid? Okay, well, this one won't be hard. But we're going to start out with, and they gave me the grams, 0.00375 grams of glucose. Okay? And we need to divide that by the grams of the, and it needs to be in grams, okay, for mass per mass percents, of the sample, which is 5.0 grams of spinal fluid. And then we're going to multiply it by 100. Okay, so what is the mass percent of glucose in spinal fluid? What is the concentration of it in mass percent? What is it? I'm sorry, I can't hear you guys. You talk so quietly.
0.075.
Okay, 0.075% glucose by mass. Okay. Now, if this question was a little different and it had said that you have 3.75 milligrams of glucose in 180 milligrams of water, okay, then I would set this up different. I would do this differently, because I wouldn't say 0.00375 in 0.180. That's not what I would do. Why? Why? Because this 180 milligrams of water is not the mass of the entire solution. It's only the mass of part of the solution. What's the rest of the mass of the solution? This. This is part of the solution. The solution is the entire thing. So I would have to say 0.1 plus 0.00375 grams of glucose. This divided by this. That's what I need to do, times 100. Okay? Do you guys see how that's different? Here they told me it's 5 grams of spinal fluid. That spinal fluid contains the glucose, right? So I didn't have to do that here. But here they're telling me you dissolved 3.75 milligrams of glucose in 180 milligrams of water. That's not the mass of the entire solution. The mass of the entire solution is both things together. It's both things. So you need to be aware of that when you're answering these kinds of questions, because otherwise you might take 0.00375 divide by 0.180 times 100 and get it wrong. Okay? It has to be the mass of everything. The mass of the entire solution. So it's always part divided by the whole times 100. Okay? So make sure when you're reading these, you're reading them to the point where you understand if it's the entire solution that they're talking about or the pieces of the solution. And you need to put those together to find the mass of the entire thing. It needs to be in grams. I mean, in this case, if you would have left it in milligrams, you would have got the same, because the units are the same. But it should, I guess it doesn't really matter, because the ratios will be the same. When we do this next one, it does need to be in grams, which is mass per volume percent. Okay? So mass per volume percent, you do need to have it in grams. It's going to be the grams per the milliliters, kind of like a density. Okay? But this is simply, you're finding the mass of the solute, the thing in the lesser amount. That's dissolved in the thing in the greater amount. But that thing in the greater amount will be in milliliters. And it'll be milliliters of the entire solution as well. Okay? How many milliliters when you've dissolved everything into the solution is your final volume? What is your final volume? Okay? That's the milliliters of the solution. So if it says into 100 milliliters of water, it was dissolved into 100 milliliters of water, well, it didn't tell you the final volume. You have to know that final volume. Okay? So calculate the concentration percent mass per volume of sodium chloride solution that was made by dissolving 25 grams of sodium chloride in enough water to make 400 milliliters of solution. So we're okay. They told us the milliliters of the final volume of the solution is 400. So simply 25.0 grams divided by 400 milliliters times 100. Okay? That's how I'm going to calculate the mass per volume percent. Mass per volume percent. It's that straightforward. Okay? It's that simple. So what is my mass per volume percent of sodium chloride in this 400 milliliters of solution? Bless you. Okay, so we have a 6.25% mass per volume sodium chloride. Okay, solution. Okay, now sometimes they don't give you. It's not this straightforward. Let's see. Did we do another question? Okay, let's look at this one. Okay, how many grams of lithium chloride are in 300 milliliters of a solution, which is 8.75 mass per volume? Now what do I do? Okay, first thing I want to do is I want to get it out of percent and put it back into its decimal. So 0.0875 equals what? Equals the mass per volume. Okay, I don't have that 100 anymore because I divided by 100. I got rid of it by putting it in its decimal. Let's start over so we don't confuse anybody. 8.75% equals the mass per volume times 100. So I divide by 100 and I get 0.0875 equals mass per volume. Now I can what am I solving for? Mass, right? So I'm going to multiply this number by the volume and it'll equal the mass. Mass equals 0.0875 times the volume of 300 milliliters. So what is my mass here?
26.25.
So I have 26.25 grams of lithium chloride. So this is a question, a practical question, because if I want to make this concentration in 300 milliliters, then I simply do this, and then I know, oh, I need to go weigh out 26.25 grams of lithium chloride, put it in 300 milliliters of water. 300 milliliters, not of water, but final volume 300 milliliters. So I would probably dissolve it into 100 and then dilute to 300 in the end. And I would know the percent mass of it, 0.875% mass per volume. Okay, so that's a practical way to apply this. All right, so here's some examples of ways that you might see these kinds of things. Like in medicine, a sodium chloride concentration of physiological saline is 0.9% mass per volume. Okay, so that's kind of an example of how you might see that. Or with your blood glucose, it's 70 to 100 milligrams per deciliter. Okay, it's a mass per volume ratio as well. Okay, here, drinking water, trace levels, concentration, and contaminants are rendered unfiltered tap water and safe for drinking and cooking, right? So you'll have parts per million, parts per billion. You don't want to have too much lead in your water, so they'll check it for the parts per million of lead in your drinking water to whether it's safe or not, those kinds of things. Okay? All right, so that's it for chapter 3. Okay? Oops. Okay, so you should be able to finish your homework now over chapter 3 for molarity, dilution, mass per volume, percents, mass percents, okay, those sorts of things. So here is the review. If you didn't get one, it's on the back table there. Okay, so go ahead and grab one. Just left it there. I was hoping you guys would see it, but it doesn't really do too much. Okay. So these are the sorts of things that you need to prepare for and know for this test. Okay. So define these terms. You need to be able to define these: pure substances, elements, compounds, mixtures. And let me just say something about the test. So this is what you can kind of focus on for it. And you'll study these items, and then you'll come take the test, and you'll be like, Mr. Crandall, I didn't really get a question about these mixtures on my test, but you made me study for it. Well, that's because you could have gotten that question. The test is designed so that it has a bank of questions, and it will pull from that bank of questions, and it will give you different questions, and it will give you different questions. So if you don't get the question about mixtures, that's because it didn't pull that one for you. But it could have, so you have to be prepared for it. Okay, you have to be prepared for all these questions. So you need to know the definitions of all these, because you might get a question over one of those. You might not. Okay, but you need to be prepared for all those types of questions. Okay, that way I can make a test that doesn't take, I don't have to test you on every single little principle, but I know that you've prepared, because you could get tested on every one of those principles. So you need to be prepared for it. Okay? Because we only have an hour, 15 minutes, I can't make a ginormous test for you to take. So it's only going to be like 20, 25 questions. Okay? So that's what you need to be prepared for. Okay, so make sure you know the definitions for those things. Pure substances, that's an element and a compound. Okay, so those are kind of grouped. Pure substances are elements and compounds. So the confusing thing about that sometimes is when you say H2O versus H2, and you ask which one is the pure substance. What's that? They're both pure substances. Water is a pure substance. It's a compound. So it is defined as a pure substance. It is not a mixture of elements. A mixture of elements would be things like H2 and O2 mixed together. Okay? H2O itself is a compound. It's a pure substance. Okay? It's classified as such. A mixture, though, is if I take a pure substance like sodium chloride and I put it into pure H2O. Now it's a mixture of two pure substances, right? Now those two pure things have become mixed. Sodium chloride and water, that's a mixture of sodium chloride and water. It's a water-sodium chloride mixture, okay? And such a mixture like this would be homogeneous. It would be homogeneous because those particles are mixing themselves. The sodium and the chlorine, they break apart and they mix throughout the entire water solution all by themselves. I don't have to do anything. Okay? I don't have to do anything to make them. So they will do a perfect job. But if I take sand and I take iron shavings and I mix them together, I can sit there all day, and mix, and I can never guarantee that the composition of the iron in the sand is completely, perfectly the same throughout the entire mixture. I can't do that because those particles are not separating themselves. I am mixing them. And I might do a pretty good job, but I might take a sample at the bottom and a sample at the top, and they'll be different. Different amounts of iron for the silicon dioxide sand at different parts, right? And so I cannot guarantee that, therefore it's a heterogeneous mixture. Okay? So that's the difference between those kinds of things. Extrinsic and intrinsic properties. It's in the name. Intrinsic means independent of the amount. Independent of the amount. So density is the mass per the volume. Density is an intrinsic property because it doesn't matter if I have a big cup of water or a little cup of water. The density of the water is the same. Density doesn't change with mass. However, which one of these cups is heavier? This one, because it has more mass. Mass is an extrinsic property. It is dependent on the amount. Mass changes with the amount. Volume changes with the amount. So those are extrinsic properties. Density is an intrinsic property. Concentrations are all intrinsic. Concentration units would all be intrinsic. Okay? Okay, so physical changes. Physical changes are identified if you undergo a change, but you don't change your chemical composition. H2O, liquid, to H2O, gas. That's a physical change, right? I am not changing my chemical structure. I'm changing my physical property. So, H2O, gas, to H2 plus O2, gas. Okay? I have chemically changed, right? H2O chemically changed into H2 and O2. That is a chemical change. So when you become something new, something different, you have undergone a chemical change. Okay? So that's the main difference between a chemical and a physical change. Physical changes retain the identity of the substance throughout the change. Chemical changes do not. They change their chemical structure. They change their chemical composition. Okay, be able to calculate mass, volume, and density from the density equation. Density equals mass over volume. Okay, so density equals mass over volume. So what does mass equal? What does volume equal?
Mass divided by density.
Okay, those are the equations that you need to use. Okay, that's how you would do that. Be able to identify significant figures. Okay, so oh, jeez. Okay. How many significant figures are in the first number? 2. How do you know? You have to ask yourself this question, because you're only asking about zeros. Do these zeros have value to them? Yes, they have value. If I take them away, they change the number, right? So they are not significant. Value, not significant. No value, significant. Okay? So this has 2. How many does this have?
4.
So really I'm asking about this one right here. Is this a valuable, does it have value to it?
No.
So is it significant?
Yeah.
So that makes all the other zeros between those significant figures significant also. So how many significant figures are in this number? 4. Okay? Do these have value to them? Yes. If I take them away, they change the value, right? So are they significant? No. So how many significant figures? 4. Okay? Do these zeros have value to them? Yes. So if I take them away, they change the number. So are they significant? No. Do these zeros have value to them? No. So are they significant? Yes. How many significant figures? 6. Yes.
If you like on the very top of like 0.00, you said the 0 before the decimal point.
Does this one have value? Is that what you're asking?
Yeah.
No. Yeah, don't even worry about that one. It's more just looking at these. That's just there to show where the decimal is. So even if you wrote it like this, okay, it's the same question, and it'd be the same answer. Before the decimal, it doesn't even matter as anything. You don't even have to consider it. Okay, it's just it's not part of the number. It's just really a representation of where the decimal is. Okay, you don't even have to write it. So really, you're just looking at these zeros right here. Okay.
Are you going to give us like problems as well, like addition, addition?
Yeah. So if you, how do you add? If I add two numbers, 0.00378 and 0.59, okay, how many decimal places will I keep? Two, right? I cut it off right here. Okay, that's for addition and subtraction. Okay, for multiplication and division, I keep the one that has the least number of significant figures. So 1.5678 and 230,000, 2,300. I mean. Okay, so if I multiply those two numbers together, how many significant figures would I keep? 2, because this has 2 significant figures. This has 1, 2, 3, 4, 5. That's 5 significant figures. So you would keep 2 significant figures in your answer. Okay, so that's how you do addition and subtraction, multiplication, and division. Okay, all right. Okay, composition of an atom. So let's just go to the next one because I think that'll answer that first one. How do you determine the number of neutrons in an element? So let's say I have P32 and P31. Let's determine the number of protons, neutrons, and electrons in each of these. How many protons are in P32? 15. You find that from the periodic table. 15 protons, that's the atomic number. How many neutrons are in P32? 17. Because it's the difference between 32 and 15. It's 17. So 17 plus 15 is 32. 17 neutrons, 15 protons equals a mass of 32. Okay? How many electrons? 15. How many protons in P31? 15. Neutrons? 16. And electrons? Okay. What if this was P3 minus?
The electrons will change.
To what?
You add 3.
You add 3.
So
18. So now it's 18 electrons. Okay. Yes?
So like some of us, when we can't see this, can we just bring it to your table?
Oh, you'll have one. I'll have one. There'll be one that it'll be a reference material on your test. You'll be able to use it.
Will it be the one with the valence electrons? Periodic table?
This is what it'll be, right here. Okay? That's the one you're gonna get. Okay? Has the names, it has the masses, it has the valence electrons, yes. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that's how you're going to count valence electrons. Okay? Hello. There we go. Okay. Know how to calculate an average atomic mass? So let's try an example here with nitrogen. Nitrogen let's say nitrogen 14, nitrogen 15, and nitrogen 13. Okay, so let's say this is 96%. This is 2.8%, and this is 0.2%. Okay, so that's 100%. So I want to find the average atomic mass of nitrogen using these percent abundances. Okay, so I have a mass of 14, 15, and 13, and so these are my masses. Okay, and I'm going to multiply them by their percent abundances, but not in percent form, in decimal form. So 0.96, 0.028, and 0.002. Okay, so these are the form that I'm going to do them. Multiply them in. I simply divide by 100 for each one of them. So 14 times 0.96 is what? $13.44. Okay. 15 times 0.028. Okay. And 13 times 0.002. Okay. You add those together, what do you get? 13.89. Is that what you said? Okay, percent. Okay. So probably the example you would get would be closer to 14 than this one, but they would have to match approximately. Okay, and that's good enough. Okay, so that would be your average atomic mass. That's the process that you would follow to find the average atomic mass of something. Know how to predict ions. So here's my periodic table that we were looking at earlier. How do I predict the ions that form? Well, everything in this first column right here has one valence electron. Therefore, the ion that it forms is what? Plus 1. It loses that electron and it becomes plus 1. Li plus 1, Na plus 1, potassium plus 1, rubidium, cesium, francium, they're all the same. Hydrogen is not a metal, so you don't have to worry about considering it. Okay. What about everything in the second column right here? Plus 2. Okay. What ion is nitrogen going to form? Minus 3. It has 5 valence electrons. It wants 8. So it's going to have to gain 3 electrons. So nitrogen, phosphorus, arsenic, they're all going to be 3 minus. Okay. Everything here under oxygen, sulfur, selenium, tellurium, they're all going to be negative 2. Everything right here in this last column, which is the halogens, or sorry, not the last column, but the next to last column, fluorine, chlorine, bromine, iodine, and astatine, those are all going to be negative 1. And these guys, they don't form ions. They're noble gases. They have 8 valence electrons. They're very happy with that. Yes?
So this is kind of an unrelated question, but I know it's not in your periodic table in this one. For like numbers 104 through the rest, they have different lettering. Is there any reason for that?
It's because the reason why, what do you mean, different?
Like with 107, it says, like on your periodic table up here, it says BH, but on here it says U.
Oh, it's just because they hadn't written anything in here. These are the kind of the undiscovered ones, and they've recently put more onto the periodic table, and so this just has a more complete. No, but that's not going to affect anything. It won't. Yeah, that's why. Okay, so that's how I'm going to predict the ions. What is the ion that will form for iron? I don't know. It could be 2 plus, it could be 1 plus, it could be 3 plus. Iron is a transition metal. You don't predict it. It's unpredictable. I don't predict the ion of iron. I have to be told what it is in the formula or in the name. Iron 1, iron 2, iron 3. That's where I find it. But I don't predict it from the periodic table. What is the charge of an aluminum? What is it? 3 plus. I can predict that one. What about zinc? 2 plus. I can predict that one because it doesn't ever change. It's always 2 plus. There are 3 transition metals that you need to know. 2 plus, 2 plus, 1 plus for silver. Zinc, 2 plus. Cadmium, 2 plus. Silver, plus 1. Those are the only 3. What about lead?
Can you go 4 plus or 4 minus there?
No, it's a metal. It's going to lose electrons. It's not going to gain them. Unpredictable. Okay? All of these metals in the P block, I can't predict them except for Al. That's the only one. Okay? But all these other ones, I don't predict. Because look what they have to go through. They have to go through the D block. So they're unpredictable. I can't predict them. So it could be lead 2 or lead 4. It could be either of those. Okay? So you can't predict it from the periodic table. Okay. Know how to predict the polyatomic ions from the periodic table, the major ones. The other ones I will give you, okay, as a reference. You won't have to know some of the other ones, but these ones I do want you to know. Okay? CO3, NO3, ClO3, BrO3, IO3. Okay? The charges of these ones right here, those are all -1. Nitrate, NO3, is also -1. Carbonate is -2. And then when you get to these two, phosphorus and sulfur, they're both SO4 and PO4. Their charges are -2 and -3, respectively. So it goes -1 chlorate, sulfate -2, phosphate -3. That's how you predict those charges on those items. Okay. Make sure you're naming. Go ahead and make sure I gave you a packet on naming. Make sure you know how to do that, how to predict their charges, to find the formulas. Main thing for naming. If it's ionic, you do not use prefixes. If it's covalent, you do. If it's a transition metal, you tell me the charge of the metal in the name. Iron 2 oxide. Okay? What's the name of this compound? It's a manganese oxide, but which manganese oxide is it? Not 2. Not 1. -2 times 2 is -4. So what's the charge of the manganese? What's the name? Manganese 4 oxide. Okay, do you see the easy mistakes that you can make? Don't make those on the test. Make sure you know how to get that charge. Yes?
So it said the 3 transition there, we know the charge that we don't have to say that.
That's right. If it's zinc, so if this was zinc oxide, then you would just say zinc oxide. You don't have to say zinc 2 oxide because we know the charge of zinc. It's zinc 2 plus. Al, you don't have to say it either. Okay? So Al2O3. That would be the formula for aluminum oxide. Okay? You don't have to say it. Okay. Covalent compounds are very simple. What's the name of this compound? Phosphorus trichloride. I do use prefixes for this one. I don't use prefixes for the other ones, for these ones. Because If you know the charges, you can figure out the formula. They can only have one ratio of those because they're charged elements. But for things like this, I can have multiple. I can have PCl3, I can have PCl5. So you have to tell me how many of everything you have in covalent compounds. Okay, acids, the main thing you need to remember about acids, if it's if it's a binary acid, you start it with hydro, blank, ic, acid. So HCl, hydrochloric acid. If it's an oxy acid, that means there's oxygen in the compound. Then you have to say ic acid for an ATE ion like HClO3. This is chloric acid. I don't say hydro this time. No hydro. Chloric acid. So HCl, hydrochloric acid. HClO3, chloric acid. So if it's an ATE ion, I use ic. If it's an ite ion, HClO2, then I use us, O-U-S, acid. Okay? Chlorus acid. Those are the rules for naming acids. Okay? That's how I'm going to name those. Let me see. I think somebody was going to come and talk to us. Let's see if he's here. Oh, not here. Okay. Okay, and then chapter 3, that's what we've been... Oh, you are here. Okay, go ahead.
I popped over there. I was like, oh, I came too early.
Oh, you're okay.
Okay. I'm going to pass out to you guys is actually a survey we're doing. So we're starting to offer supplemental instruction for chemistry. It's a new program.
Bring your laptop. And if you go to there is even if you try to take the test, it's not going to let you. It's going to say you don't have the right browser. So it'll allow you to download the browser, and then once you have it, you'll be able to access the test, and then it's going to say, or actually I don't know if it's going to get to that point because you might have to have the code first. But there's another quiz that I put online here. So if you just go to your home page, which is your syllabus page, there's a quiz right here called Lockdown Browser Quiz. If you click on that, it'll allow you to download the Lockdown browser, okay, and get it onto your computer. And then if you open the Lockdown browser, because that's the other thing you would have to do, is open the Lockdown browser from your screen. You would open it from there. It's not going to let me because I have certain programs running that it won't let you run, like the one to record this session. It's not going to let you record things, so it's not going to let me open it. Okay, so I'd have to close that first, and then I could open it. It would take me right to ACES. I'd be able to log in and then take my test from the Lockdown browser. If you're using Chrome or Internet Explorer or Safari, it's going to say, or Firefox, it's going to say, hey, you can't use this. You have to use the Lockdown browser. Okay, but that's how you're going to get it. All right, so get that downloaded. Bring your computer. For those of you that won't have a computer, I'll have some available for you to use, okay, that already have the Lockdown browser on them. Yeah, we'll see you guys Monday. Good luck.